You're live.
Good morning. It's a great pleasure to be here. I hope everyone is enjoying Uppsala and all the different activities around it. It's been a really different experience for me in using Clouder, etc. It's a real pleasure this morning to introduce Emery Berger. I've known Emery for many years, and he's a professor at the University of Amherst, University of Massachusetts Amherst, where he co-leads the Plasma Group. His research is broad. It spans many different topics, including programming languages, systems, security, and human-computer interaction. And one thing about Emery's work, it's well known for the impact it's had on real systems, including languages like Rust and Swift, and large operating systems, mainstream operating systems like Mac OS and Microsoft Windows. The other thing to understand is Emery is very dedicated to his service, his professional service. He's been just very, very involved in various activities around helping students and helping the review process of computer science, including developing and maintaining the website csrankings.org. He's also the recipient of numerous awards, including multiple most influential paper awards and CACM research highlights. And for that work, he was named an ACM fellow in 2019. So if you haven't heard a talk from Emery before, it's going to be a real pleasure for you, I guarantee. And if you have, you know what to expect. His talks are always informative, capture your attention. And with that, I give you Emery Berger.
Thank you, Ben, for your very, very kind introduction. All right, so this talk, I hope you didn't set the expectations too high. So this talk is on performance. It's performance really matters. And part of this work is joint with Charlie Kurtzinger, my former PhD student who is faculty at Grinnell College. All right, so most of you will be familiar with this family. We've kind of spent the last couple decades with them. So this is what this family looks like in 2020, right? So this is the Simpsons you've all come to love. But it turns out in the 80s, the Simpsons, when they first appeared, were a whole different family. Really, maybe not as attractive and polished and nice. And, you know, so a lot has happened to the Simpsons in 40 years, and a lot has happened to computers in 40 years. So today, you know, you have your phone. Your phone is this incredible powerhouse. It's, you know, typically almost 3 gigahertz times 6 cores. You've got a 64-bit processor, 4 gigs of RAM or more. And you compare this to the 80s, you know, this is an IBM PC from 1981, 4 megahertz, not gigahertz, 16-bit processor, and 640K of RAM, which, as everybody knows, is enough for everyone. So obviously, you know, things have changed quite a bit. This is effectively a 3000x increase in computing power. So that all started in the 80s and kind of accelerated up until the current day. Before the 80s, however, computers were pretty slow. And so essentially, if you wanted any performance at all, you had to write programs that really were close to the metal. So the first language on the left, 1949, is assembly language. And we have Fortran, the C programming language, and C++. And you can see these were all introduced really stopping in the mid-80s. And I like to call these metal languages. These were developed in an era where computers were slow, where the resources were scarce, and you couldn't afford to have any sort of inefficiencies. And really, ruling out inefficiencies was the name of the game. However, in the following decade, we had this set of other languages, which I'm going to talk about, which are these irrational exuberance languages. And so I will get to those in a second. So in essence, we had this 40-year performance ride from 1980 until 2020, where things were getting faster and faster. And so this is a graph all of you will be familiar with. The left side is number of transistors in millions in log scale. On the right is clock speed. And things were going up linearly on both sides. And of course, because the features were getting smaller, we were able to clock them up. And if you bought new hardware, your code would just run faster. And so what happened is that while people had been using metal languages, we came to an era where people could use these, like I said, irrational exuberance languages. And these all appeared pretty much around the same era. And they appeared at this time. And again, here's sort of off to the side is JavaScript. They appeared at this time when computing resources suddenly seemed like they were going to get faster and faster and faster, and we could afford inefficiencies. And so people decided, well, instead of focusing exclusively on efficiency, let's focus more on productivity, or in certain domains where we felt like performance didn't really matter. So in this talk, I'm going to focus on Python. So Python is a somewhat fat language, like many of these dynamic irrational exuberance languages I was talking about before. So for example, the number of bytes in an int, if you're using a meta language like C++, the size of an int is 4 bytes. And if you use Python and you ask how big it is, it's 24 bytes. The reason for this is in Python, every object carries a bunch of information. Everything is unboxed. And this makes things a lot fatter in terms of memory consumption. Here are a few more examples. An empty list in C++, 24 bytes. In Python, it's more than twice as much, 56. An empty dictionary, again, 24 bytes in C++. In Python, today it's 64 bytes, so a little less than 3 times the size. But recently as Python 3.6, it was 240 bytes, which is a curious coincidence. It's just 1 byte more than how many pounds Homer weighs. So I hope I've convinced you that Python can be fat. It also is notoriously not fast. It is a famously slow language. It is interpreted, although there are implementations that do JIT compilation. It's still considerably slower than native code. So here's a little example. This is naive matrix multiply written in Python. And this graph shows what happens when you move from Python to C to optimize C and heavily optimize C. And the point that you see on the far right, that is 62,806, is about the speed difference between using the Intel optimized BLAS versus using Python. So it's a 60,000x gap. That's a lot, right? And things like PyPi can't actually recover anywhere near that kind of performance. I actually ran this with PyPi, and it sped it up by 10. But again, this is 10x versus 60,000x. So that's quite a difference. So, this kind of performance gap probably felt reasonable at a time when performance was going up and up and up and up, like, like we're inching up the roller coaster, although it was going, in terms of clock speed. It's an analogy. But of course, starting around 2010, the ride ended, right? And it ended pretty spectacularly. So if you had stretched this out, again, you all are familiar with the story, the number of transistors, in fact, continued to grow as expected. So transistor count still increased. This is Moore's law. But unfortunately, we found ourselves in a situation where Dennard scaling ran out. So we're unable to produce chips that actually are clocked up as high as we wanted because they basically get too hot. So, in the 80s, being a performance engineer was pretty sweet. You could actually just kick back, drink a Duff beer, and wait for faster hardware. Your program was going to get faster. It's going to double in speed just by you sitting around and waiting. But modern day performance engineering is much harder. So the only kind of Duff that is available or useful now is an energy drink. Kicking back is not going to work anymore, right? So the hardware is just not going to get faster. So what about optimizers? So I'll explain why that actually also doesn't really work. It doesn't work as well as you might think. So, this is the way. So Homer has some code, decides to look at this code and make it run faster. So Homer has an idea. It's like, oh, I'll refactor this code. All right, I won't do a Homer imitation. I'll refactor some code. I'll move some around. I'll optimize this function. And then I get a new function, A prime, or new program A prime. And then Homer says, well, which one is faster? Right? So he runs A, it takes 90 seconds. He runs A prime, it takes 87.5 seconds. Great, A prime is faster. Woo, 2.8%. All right, so why is A prime faster than A? Well, of course, whoops, oh, so many animations. Because it's a code change, because Homer was a genius, right? Unfortunately, it could also be because when Homer made all of these changes, he just moved stuff around. And moving the stuff around actually led to the performance improvement. And the reason for this is that layout biases measurement. So there's this lovely paper by Todd Mitkowicz et al. hell, I'll read their names. Todd and Amr and Matthias and Peter. And it's a great paper. It's called Producing Wrong Data Without Doing Anything Obviously Wrong. And it shows that there's a bunch of things that you can do, essentially poking at a program, that have very large effects. So if you change the link order in a makefile, that changes function addresses. That moves things around. If you change the environment variable size, that will end up moving the program stack, which will move everything else in memory. And it turns out that the impact of these things can be larger than the impact of -03. So this is pretty substantial. So what's happening here? What's happening is in the first version of the code that Homer wrote, you might be in a situation where the hot code was mapped to the same cache set, and you had conflict misses. However, just by moving it around, you could get lucky, and then the hot code is no longer mapped to the same set as anything, say, and so because there's nothing there, there's no conflict. So that's great, if it works out, right? So it's the cache, and if you get improved performance, that might seem like a good thing. But remember, anytime you change an environment variable, anytime you change link order, any new code you write, any new malloc can screw this up again. And it's not just the cache. It turns out that modern hardware is super complicated, and understanding what's going on is really difficult. So other things that depend on program addresses or memory addresses are branch predictors, TLB, the branch target predictor, prefetchers. All of these things are implicated, and you can have effects that are positive and negative just by random chance. So it turns out we were able to create this the system that we call stabilizer. Stabilizer allows us to actually tease apart the effect of optimizations from the effect of all of these random changes of the impact of the layout. And what we observed, this is my one slide summary of stabilizer, what we observed is that -03 versus -02 has practically no effect. Some effects are significant, but we're talking a couple percent. And that couple percent is a lot less than the impact potentially of moving around code. So this is a bad situation for people who are trying to improve their program's performance, right? So we can't expect the hardware to get any better fast. We can't expect, or we can't rely on the compiler to optimize our way out of this mess. So what are we going to do? So let me walk you through a situation where Homer is going to develop an application and then actually be able to analyze it properly. All right, so Homer has an idea for an app. It's a great idea. It's basically you take a picture of something like a cat, because the internet, and then the app returns a bunch of similar images that are, again, cat memes. So perfect. This is the best internet app idea ever. And he has a great name for it. He's going to call it Ogle. And he's convinced that it's going to totally disrupt image search. He's not aware of images.google.com, but that's okay. So goes and plans out the prototype Ogle, right? Here's how it works. You take a picture. It gets sent to the Ogle servers. The picture gets added to a database, so it can be used later. It goes and finds similar pictures and sends them back to the app. All right. At a high level, I'm going to use this like a graph notation to show what the program looks like. In effect, there's two parallel threads going on. One of them does some sort of image compaction, saves the image to a 3.5-inch floppy disk, as one does, performs some indexing to actually go and do the search, performs the search, and then sends it back to the user, right? And then there's kind of an implicit join here. Now, I've obviously simplified a number of things because you've got access to a database. Databases are concurrent, and you have to be careful. So there might be locks involved. So you're going to end up with some sort of locks. But anyway, so obviously there's more complexity here. All right. So suppose Homer deploys this app and discovers that it's slow, right? So Ogle is too slow. So what is he going to do about it? So the right thing to do now is to go to get a software profiler. So software profilers are supposed to help you find performance problems. So here is a typical software profiler. Roughly speaking, of course there's variants, but they generally work kind of like this. So they track the number of calls to every function. They track the runtime for every function. And the insight is, hey, if I see something that's frequently executed and it runs for a long time, that's where I should spend my optimization efforts, right? So things that don't run hardly at all and are rarely executed, probably you shouldn't focus on, but things that take a long time, yes. right? So it seems like this is where Homer should focus on performance. So let's apply this to Ogle. So Homer goes and looks at Ogle and spends his time identifying the thing, according to the profiler, that takes the longest time and runs most frequently. And then he improves the speed and he deploys it. And unfortunately, what happened is that blinky thing that shows loading is actually frequently executed, and it runs for a long time. It runs, in fact, longer than anything else, right? It's this from the start to the end of the whole execution. So obviously, it's a contrived example, but I hope it convinces you profilers don't necessarily do a great job of finding the important code in applications that are parallel, asynchronous, or concurrent. So we need to be able to do better. So what would speed up Ogle? Right, so you look at these components, it's obviously looking at them like this is not going to help you very much. What we wish we had is some kind of magic pixie dust that we could sprinkle over the program. And some of it would stick like glitter onto the thing that we really had to pay attention to, maybe even specific lines. And you'd look over there and you'd say, oh, great, that's what I wanted to work on. Right, so what would that information look like if you didn't like glitter? So we have this notion of what we call a causal profile. So causal profile is going to tell you where optimizations make a difference, again, without glitter. And so the idea is what we're going to do is we're going to get a graph. The x-axis will be speed up of a particular line or component, and the y-axis will be speed up of the program as a whole. And so here, for example, this graph would tell you in the search component, if I optimize it a little bit, I get a pretty big bang for the buck. Optimize it more, still pretty good, and then it tops out, all right? And I could discover that optimizing compression has no impact. It's just simply not a bottleneck and has no effect on performance. And then I could discover that the indexing operation, the more you throw at it, the better it gets, but really low-hanging fruit is search, all right? So the insight again is, if you had a graph like this, it would provide the following information. If you speed up this component by this much, like the red one here, then you would get this much improvement in your program. All right, great. So we have causal profiles, but how do we get them, right? How would we know that this change causes this effect, right? So what we could do is we could run an experiment. And the way we would run this experiment would be, we would just basically go through all the possible data points and magically somehow speed up each component by a certain amount, and then observe how much it sped up the final program. All right, so again, this would be great. We'd have to do it for everything, but we, we'll magically speed this up a little bit more. We get the next point, right? Then we discover we get more speed up. At some point, right, it runs out of steam. We can do this for everything, right? Discover, oh, this has actually no impact on performance and so on. So this is great, but unfortunately, magic is actually not a thing. If it were a thing, if we already could magically optimize all the code, we would just magically optimize all the code, right? So that would be magic, and we can't do it, right? But it turns out, like I'm really good at, maybe I'm not as good as performance engineering as I'd like to be, but I definitely know how to slow things down. And so what we're going to do to get our causal profiles is to produce this effect that we call a virtual speedup. So virtual speedups work by slowing everything else that's running concurrently down. And so what we do here to speed up the mailing back, you slow down everything that's running concurrently and you observe the slowdown. And it turns out this is the same thing as, it's a question of relative speed, right? So, this one is faster, to make it faster, you can just slow down the thing that's running next to it, right? Okay, so this is what we do. We go ahead and we slow things down. And for details on the mechanism, I'll point you to the paper, but we do this over and over and over again, randomly sampling execution. We observe these changes, right? We see, oh, a larger speedup has no additional effect. We end up graphing out the points, and eventually we get a causal profile for the whole program. And you can see, there's some interesting cases here. The most interesting to me, not only are there good ones that go up, but there's one that actually ducks below the 0 line, and that's the compression. And it turns out we observe this in practice, where optimizing some part of a program in a concurrent program can actually lead to more contention, to more false sharing, to all these other effects. And it would be good to know this in advance without, imagine you spent a huge amount of time trying to optimize some code and then it ended up slowing your program down. That would be bad news. So you would want to know this kind of information. All right, so let's go ahead and apply this to Ogle, right? So here's the Ogle app. What do we care about for Ogle, right? So we don't care, like for traditional programs and profilers, they actually just measure end-to-end execution time. But for Ogle, Ogle's going to run forever, right? We don't want Ogle to terminate more quickly. That's not really our goal here, right? So the metrics that we care about are things like how long does it take between the time the user pushes a button until they get a response, right? So this, of course, is latency. What they also care about is maybe how much throughput there is, right? This is certainly something that can matter if you're doing a bunch of them, and that's how fast the results are coming back. So with causal profiling, you need to do one more thing if you want to be able to understand not end-to-end performance, but latency and throughput. So suppose you want throughput here, Homer just wants to send responses faster. What we're going to do is we're going to say you, as the programmer, can put in, wherever it is you want things to happen faster, you put in something we call a progress point. And a progress point just basically keeps updating every single time the code runs. And now the effect that we're looking for is, if I speed up some line of code, what is the impact on the rate at which those progress points progress, right? So we collect all this information. It runs simultaneously, right? This is some multi-threaded program. And one progress point will then measure the throughput for the entire application. And we will get the answer to our question in the causal profile. If I speed up a component, how much faster do I run this particular thing? What is the throughput of the system? Likewise, for latency, if you want to minimize response time, you can add two progress points. So we have a special progress point for latency. By the way, these are all just macros that you put in C or C++ or Rust. So you add these latency progress points, one at the beginning and one at the end. So the first one is the start of the request, and the last one is the end of the response. It basically keeps track of the number of transactions in flight. And this turns out to be something that allows us to recover latency. So normally latency is difficult to obtain because you need to track information about which job is running and observe the beginning and the end, and you have to plumb it through a system. But there's this nice result from queuing theory called Little's Law. And it turns out that latency is just equal to, on average, the number of transactions divided by the throughput. So we basically use the same throughput trick, track it, keep track of transactions, and now we have latency. So we can produce causal profiles for throughput or for latency. So we've implemented causal profiling in a profiler that we call Cause. It ships with Debian and Ubuntu. So you can install it as follows. And the way it works is you say cause run, then 3 dashes, and then your program and its normal arguments. And when you do this, it performs a bunch of random performance experiments. And their randomness actually addresses some of these issues of layout. And I don't have time to talk about this right now, but I'd be happy to address it in Q&A. All right, so let's go ahead and use causal profiling in Ogle. So we didn't really build Ogle, but we took a bunch of off-the-shelf components that do all the different things that, that Ogle does. So I'm just going to show you a couple results. So this is a causal profile for Ferret, which is an image indexing thing. And you can see that it shows some lines of code that we should speed up. And it's a reasonably constant amount of speed up for each of these. So it's like, well, if we could give more resources to this we would. It turns out that these actually correspond to separate components within Ferret. Ferret is a pipeline-based architecture. It takes in input, it segments it, does this feature extraction, then it does the indexing, it ranks the results, and it sends them out. So it's all in this pipeline. And the way that it works by default is, in fact, the way that it's built is you have an argument, which is the number of threads, and it assigns the same number of threads to every single stage in the pipeline. But we now know exactly what we want to do in terms of optimizing. Certainly, we don't need as many threads in feature extraction. So we basically used the causal profile, figured out how many threads proportionally should be devoted to each thing, and this alone led to a 21% speed up. So we didn't even have to change hardly any code. We just had to put in a little plumbing that said, use this number of threads, this number of threads, this number of threads. All right. So the nice thing about this is that doing this actually made it quite easy to validate whether cause was doing what we hoped it was doing. So in ranking, for example, we increased from 16 to 22 threads. This led to a 27% increase in throughput. And if you look at the causal profile, this right here turns out to be 21% performance improvement predicted. And that is exactly what we observed. So it's really doing a good job. Mostly this is just a, the effect of these random experiments tends to average out noise and produce reliable results, which is great. So we did this for a variety of these different components. I'm gonna also talk briefly about Dedup just because it's so damn funny. So this is the compression thing. So the way that the Dedup does compression is via deduplication. So if you have a picture and then you have a meme that looks a lot like that picture, it's just the meme text on top of it. What Dedup will do, it'll identify the components that are the same, and then it'll split images into basically pointers to segments. So now Grumpy Cat 1 is split into 3 pieces, and Fun is Awful is split into 3 pieces, and they share a piece. All right, pretty straightforward. So the way this works is through, unsurprisingly, through hashing. There's a bunch of buckets. You compute a hash function on the image, and if there's nothing there, you put it in the bucket. If there's something there, then you chain it. All right, so you just keep doing this over and over again, and eventually you get stuff all piled up into the different buckets. So it turns out this hash table is accessed concurrently by many threads, and they didn't do it entirely stupidly. It's naive, but it's fine. There's a lock for every bucket. So fine. So interestingly, Cause said that the loop that accesses this list is important, which was surprising because the way that the hash tables work, this is not supposed to happen, right? They're supposed to be balanced. So what we did is we drastically increased the number of buckets to try to lead to fewer collisions. This led to no performance improvement. And you probably know the answer to this question. What else can cause a collision if every bucket has its own lock, and increasing the buckets doesn't cause any improvement? And the answer turns out to be the hash function, which was hand rolled. We did it. This is a histogram of the utilization of the buckets, and you can see they're very skewed. In fact, they're normally distributed, which is not what you want. You want a uniform distribution. The reason they're normally distributed is that the hash function actually added up pixel values, and this led to a normal distribution. So we replaced the plus sign with the XOR, and with a 1 character change, we got the bin utilization to 82%, and this led to an overall speed up in the program of 9%, which is not huge, but 1 character change, 9% speed up, not too shabby. So what did Cause predict? Basically we know what the effect was in terms of the number of blocks per bucket. So the blocks per bucket on average was 76.7. After we fixed the hash function, it was 2. This is a 96% traversal speed up, and the causal profile predicted a 9% speed up, which is what we got. All right, I'm not going to talk about the others like SQLite, but this is a summary of some of the results, and we ran it on a bunch of programs, and we were quickly able to find performance bottlenecks and resolve them. All right, so this is great. I highly recommend you use Cause if you're writing any code that is written in one of these metal languages, C, C++, or Rust, and it's really great for finding performance issues. All right, so like I said, it's great for metal languages. Somebody has actually implemented a Java version of Cause, and Cause out of the box works for Rust, which is very scary for Bender. But what about these irrational exuberance languages like Python? So Python is not great for performance, as I pointed out before. And really, your only hope is if you are writing Python code and you want performance, you need to move your Python code into C. That is to say, you need to be able to take advantage of all of these great libraries that are out there. They're actually written in metal languages. But right now, it turns out profilers don't help you in any way to understand the performance of your program and how you should really optimize it. So what I'm going to talk about next is what we've been working on for optimizing Python, but we actually think that many of the concepts here are broadly applicable to scripting languages in general. So this system we call Scalene, and this is about scripting language-aware profiling. So the way that Scalene works, you just say Scalene and your Python program and whatever arguments. It has a CPU-only mode, which I'll explain later, where it only does CPU profiling, but Scalene does a bunch of profiling, including memory profiling, which you'll see in a minute. If you say --HTML, it produces a lovely HTML output. And for a list of all the flags, of course, help. So here is a little piece of example code that somebody sent me, and it's using NumPy. It's just a little benchmark to basically, they're trying to understand what was going on, and had a question for me as to what exactly is happening here. And so if you run this with Scalene, this is the result that you get from Scalene. So Scalene has a bunch of different columns. This is Scalene in its full-blown mode. And let me walk you through what all of these say. So first, it splits off CPU time into Python time, so time spent in the Python interpreter, or JIT if you're using PyPi, time spent in native code, so running a meta language, and then system time. So this is pretty fine-grained information at a line level, telling you exactly where your time is spent. It breaks down memory usage. How much of the memory usage comes from Python, and how much memory net are you consuming? This little thing here, these are spark lines that show memory consumption over time. And so the one on the top is memory usage for the entire program. You can see it reached a maximum of 1 gig. And then each line has its own individual information about memory consumption. We also have this new profiling feature, which is something, again, that is specific to scripting languages. Scripting languages, when you are using one of these libraries like C, that are written in C, like NumPy, you end up copying stuff back and forth across the boundaries between Python and C. And that's something you would like to avoid as much as possible, because copying can be quite expensive. You can see that this line of code, in addition to consuming a bunch of memory, also produces a ton of copying, 120 megabytes a second worth. All right, so look at this line. This is clearly a bad line. This is one of the places where we really want to work on optimizing our code. But let me draw your attention to the fact this is not the most. This is not where most of the time is spent in the program. Most of the time is spent on line 5. But line 5 is already native code, as you can see. It says 60% native. So 60% native. What are you going to do to improve native code? Not too damn much, right? So this focuses your attention on the next thing, which is this line of code, which is a lot. 34% native, but something is going on, right? So, okay, 34% of the runtime of the whole program is in native code. That seems good, right? It's not wasting time in Python, but it's allocating a lot of memory, and it's a ton of memory activity, right? And it's allocating and then freeing and copying a bunch of stuff, all right? So what's happening here is actually pretty typical. So in this case, it turns out that if you say np.array, np.array takes its input argument and converts it to a NumPy array. But NumPy is not too smart, rather surprisingly. This clearly should be fixed in NumPy. If it already is a NumPy array, it should not change it, copy it back to a NumPy array. But what's happening is it's allocating a whole new array, copying the existing array into it, and then destroying the other one, which accounts for the sawtooth pattern. So we took this code, and transformed it by removing the np.array, which was unnecessary. And so now you just have a direct call to np.random. And you can see that the time has plummeted. The memory consumption overall is still the same, but the memory usage pattern has changed quite a bit. It's gotten a lot better. So we've dropped from 1 gig to 800 megabytes. And then we dropped from 6.3 seconds to 5.4 seconds. So this is just an illustration of how this all works. Like I said, it provides all of this detail, which is great. It also does it surprisingly quickly. So scaling depends on sampling, and I'll explain a little bit about that. But basically, this is a comparison to a bunch of Python profilers. There are quite a few. So they are normalized to the execution time of the program itself. So if you look at pprofile det, that means it runs 35x slower when you use that profiler. And the points on the right Scalene CPU and Scalene full show that it's 10% degradation or 30% for the full profile information, which we think is more than reasonable. It's especially the case because none of these actually profile memory. They also don't profile copy volume. They don't separate out native time from Python time. They don't have system time, right? There's a lot of information that these tools don't provide. But memory profiling is especially awesome because there's a thing called memory profiler. And memory profiler leads to 152x slowdown, whereas Scalene only is a 30% slowdown and gets you the same information. So this is a pretty big gap. We were quite happy with this result. So one of the things I want to say about this is that this was not trivial to do. Python is a kind of a rough environment in a number of ways to extract information from. And especially you need to understand what we did not want to do was to change Python. Because if you change Python, nobody's going to use your Python. Emory's Python is not going to be very popular. So here is just one example of this kind of challenge. So in Python, so Python has signals. So it has support for signals, which is great. And you might think, oh, sampling will be terrific. We'll just set an interval. The signal comes along, signal comes along, signal comes along. You record where you were, and then you attribute that time, right, the fraction of that time that you spent in the whole program to the number of hits that you had. All right, so this seems great, and in theory would work out fine, but it actually doesn't do what we would want it to do because Python actually defers signal delivery until the Python interpreter regains control. This is very, very common, really ubiquitous among scripting languages. So what that means is that during the whole time C++, say, is executing, like in the form of NumPy, which is actually Fortran, but anyway, essentially no signals are delivered. So it's as if the program just went to sleep during that whole time. This is not very helpful, right? So we have a program, if it spends its time in NumPy, we'll just miss all of that execution and report something potentially misleading to the programmer, and that's no good. So what we realized is that actually this gives us this apparent disadvantage, this apparent problem gives us something we can leverage, and we can actually extract the information we need. So what we do is every single time we take a signal, we record the wall clock time. And so here we have the wall clock time before and after, and we see what the delay is. And then we basically use this insight, look, if we're running in Python, then the time is just going to be the interval. But any delay is effectively due to C. Now, the math in here may be a little surprising. There's a proof in the paper that shows that this works. And then we have empirical analysis. It turns out we can do this not only to capture the effect of the execution time of C or C++ code, whatever is written in one of these libraries, but we also can extract virtual time by doing the exact same trick, where we go ahead and we record the virtual time before and after and update the delay. And this gives us the amount of time spent in the system. So here, this is just to show you that this works. Here's a little program that is meant to spend 0.7 seconds in C and 0.3 seconds in Python. And this is all calibrated with these numbers to make sure it works. And so you can see that this part is taking roughly 30%, and that's the Python time. The 70% time is almost 70% is the C time. So the error is just 1%. So we're looking at extending this to other irrational exuberance languages. They all share characteristics, which in principle should make it possible for us to adopt their techniques without actually having to change the underlying programming language. Right now, we have an initial proof of concept for PHP, and I know that somebody on this call is looking into doing this for R. So in conclusion, Scalene, you can go look at it on GitHub or install it with pip. It's precise and fast. So if you just do pip install -u Scalene, you'll get it. This is a good way of dealing with Python and helping you steer you to making your Python programs run faster. And again, we hope that this is something that we can extend to other scripting languages. And of course, if you're using a meta language, then you should use Cause. And with that, I'm going to conclude, and thanks for your attention.
It feels a little weird to be the only person clapping. But anyway, thank you so much, Emory. That was really insightful, really interesting perspective. I think everyone can benefit from kind of your historical view of these language evolution, and also, a kind of amazing thing, I think, relative to understanding the tooling. I mean, from my point of view, this observation that, there are other Python tools out there, but yours is better in these different ways is really interesting. And let me just start some of the questions along these lines. So, one of the things I wonder about is, to the degree to which people who use these languages actually have an interest in things like profiling. And, so the first question I guess I would ask is, do you feel like there's an absence of interest in this kind of ability? And, and let's follow from there. But, why is it that, Scalene is such a better tool than what's out there?
So let's see. So it's an interesting question. I mean, there actually is a report, and I can't pull it up right now, but it was an extensive survey of Python developers and asked them what kind of tools they use. And it's true that it was something like on the level of 20% of users actually use profilers. Turns out more people use debuggers, and most people, they primarily use, like reformatters and sometimes things like MyPy, which is a type checker.
Mm-hmm.
I think that my experience with programmers, certainly people who only have an undergraduate degree in computer science, many of them have never been exposed to profiling. They don't even know what a profiler is, right? So they don't even have the background. So that's one issue that I think makes it so that people are let's say, not using profilers as much as they should. But then your question is really, why is this profiler so much better? I mean, obviously it's because I'm a genius. So no, I mean, look, there's a million profilers for Python. I mean, there's one of them, it's called Yappy. Yappy stands for Yet Another Python Profiler.
Okay.
Okay, so there's a lot. I mean, I think that the reality is that with few exceptions, these things are essentially, they're basically the progeny of prof, right? So prof and gprof essentially are like, we did this stuff. It happened in the 70s and the 80s, and people are just porting those ideas forwards.
Yeah, right? I was going to say, I'm guilty of that mprof in 1988. So,
I mean, it's totally reasonable to build on that work, but
that was like 40 years ago. So.
Yeah, exactly. So that work was obviously great and hugely influential, but I think it kind of just misses the boat on what a Python programmer or somebody using one of these scripting languages really needs to know.
Right. But again, so this is really interesting because I think that's a great observation. And it's kind of shocking to me that if you think about all the cycles, burned on Python in the, around the world every day, that, some kind of even basic understanding or visibility to why those other approaches aren't useful, or that what the cleverness that you brought to Scalene isn't something that is both highly valued, right? The question is like, why can't you sell Scalene for a lot of money?
My kids ask me this question all the time.
But so let me just go back to the point about education, which is, why is it that students in school don't, as a sort of core part of their education, learn that using tools like Scalene are like should definitely always be there, right?
Right. Yeah. So I mean, I think the question is where it fits into the curriculum, probably. Like, I mean, thinking about this as a professor, you have to, there's some sort of curriculum that the students are all taking. What is the class where this appears? Does it appear in software engineering? Sometimes we have these classes that are kind of more methodology focused, like, how to be a developer in a sense, kind of applied software development. That would be fine. But yeah, I mean, I think that there's not necessarily a culture around this in computer science departments as well, right? So, you have to be in a pretty systems-oriented computer science department to have faculty who are familiar with things like cache misses, right? Like,
oh, really? Okay.
Yeah.
I think that's kind of excusable in the 10 years ago or 15 years ago, where you were in this stage of Moore's law, just pushing the performance forward. It seems at this point in time, given that we're, both it costs a lot of money and we're not seeing any, dramatic improvements in performance, that departments might want to rethink kind of, what is really important in terms of teaching people to be effective. And, I agree. I mean, there's always been this trade-off between kind of just make it really easy, like convenience, things like JavaScript where it's very easy to do many things. And make it fast. But I also think that it's it's interesting with something like Scalene or Cause. I think it's really not that much effort to use it. It's sort of like you have to know that you need to use it, and you have to know it exists. But I think that the ability to teach people that is part of what they do, and this is just a normal thing. I think that should be there. I mean, it should be part of the basic training of software developers.
Yeah, I mean, I think it's an interesting question. I mean, especially the milieu in which Python lives. You've got people who are data scientists or people who are doing machine learning. They're generally not particularly familiar with how machines work, and maybe they shouldn't be. So, they're things that I've seen. I mean, so with data science, you really do want to know, hey, is this code IO bound, right? And it's like, well, if it just tells you here's where your program spent its CPU time, it's not really useful, right? And with machine learning, obviously a lot of stuff gets shifted off to the GPU. For Scalene, if that's happening, that's accrued as native time. So that's good. All you care about is the stuff that's not native. Right?
Well, yeah, and that's also, I mean, there is a separation of concerns. It's like there are things you can fix as a developer, and then there's all the stuff that happens in the in the low-level code, which you can't really change. So at some level,
yeah, I mean, some people can. I mean, there's some people, there are library developers who would like to know some things, and certainly this kind of like dumb inefficiency about NumPy not keeping track, not putting an if statement in, and seeing what the type is of the input argument. That kind of thing could be useful information to send back to developers. But yeah, this is really intended for end users.
Yeah. So anyway, and just to open this up to everyone on the call, the question answering session is an extended period, and also this is an Ask Me Anything session. So basically, this is your chance to ask Emory what he feels about almost any subject, and I guarantee you'll get a well-informed and strongly held belief about many different things. So
sometimes on both sides of the issue.
But let me shift a little bit. I mean, I think that the ability to go in with something like Cause and take existing applications and improve them by that amount with relatively small changes, it just suggests that there's a lot of low-hanging fruit here in terms of even for open source software. I mean, one question I guess is, have you thought about a service that would just automatically do this to GitHub repos? Sort of like basically. I mean, when you think about automation and scale, right? I mean, these repos are just sitting out there.
Sure. I mean, the challenge, as always with dynamic analyses, is that you need inputs. You need to run the program. And so that's why static analysis is so attractive in many ways. You don't need inputs, right? You can just go ahead and take the program source and apply an analyzer to it. It's certainly possible that one could run these things, but you would need something that said, run me.
Yeah, it's an interesting point. I mean, I think that at some level you could create a. I mean, again, it's a chicken and egg thing. People have to like offer you the API that allows you to do that. But on the other hand, if they do, they get this benefit that all of a sudden somebody's going to send them an email saying, "Hey, why don't you fix this line of your code?"
Right. And, well, there is one missing piece. So the one missing piece is the metric of goodness. So what is it they want to do? What do they want? Where is the part in the code that they want throughput to increase? Where's the part in the code where they want latency to be reduced? So that kind of thing. Actually, I feel like it's kind of a weird thing that it doesn't exist in general. I mean, we have this thing for Cause, and we use it. We basically change the virtual speedups and observe the effect on these dependent variables. But really, I think like operating systems would like to know, like if I schedule you, if I give you more memory, does your throughput increase or not?
Right.
Right? Like if your throughput doesn't increase when I give you more memory, why am I giving you more memory?
So it seems like this kind of line of talking relates to this notion of auto tuning,
Mm-hmm.
because ultimately, and this is white box auto tuning. There's a fair number, and of course in the ML space, there's a bunch of auto tuning capabilities.
Sure.
I guess at some level, it is about sort of inserting points where there's some human intervention that sort of says this is important, and then and then just handing off the optimization to a different automation system.
Exactly.
Yeah, and it seems like there's sort of the and there's a lot of talk about software. What is it? S, I mean, it's early.
Yeah, I know. Is this the
There's
2.0 kind of thing or something else?
software 2.0. There's this talk about sort of taking code that has these arbitrary constants embedded in it and sort of automatically inferring them, using a data-driven approach. And I think that it's the same kind of thing that you could imagine. If there was a framing for this, you could get a virtuous cycle where people that get the benefit, do it, and then they tell their friends, and so you have this kind of viral aspect too. And so all you have to do is say where you think the problem is, and people will then go and then some magic will happen, and you'll find out what
Right.
Yeah.
So I mean, we're actually looking into this kind of thing for operating systems. See if this idea has legs.
Oh, cool. Okay, yeah, I like that. So there is a question on the chat from Alexander. So what do you think about the relation to PGO? I assume that's profile guided optimization.
Sure. So with respect to what we were just talking about, I guess. So profile guided optimization. Again, the way that profilers, compiler-based profilers typically work is, again, they're looking at end-to-end execution time. And the thing is that most of the programs we care about, we don't care about end-to-end execution time. Like, I don't want Chrome to exit faster, right? That's not helping me, right? Like, servers run forever. So we have different metrics of interest. Now, if you can annotate those things, then you could imagine that you could optimize them. But again, we're talking about the compiler. Yes, you can get compiler optimizations that improve things. Maybe it's totally accidental, but at least it's data driven. But yeah, I mean, the extent of gains that you get from profile-based optimization, it's rarely about CPU performance per se. I mean, I think it's really about, does this fit in the iCache better? Does this all fit in RAM better? Do you avoid TLB misses? Like those kinds of effects. I know that Microsoft did this, at least. I don't know if they still do, where there's the basic block of reordering. And it was essentially like, keep all the basic blocks together so you don't go out to the disk to go fetch them.
Yep.
Right. And that turns out to have a big bang. And so that's great. And, that's totally reasonable. And you should do it. But yeah, this is certainly, as described with Cause, it's not automatic, right? With Cause, it's like, I perform experiments. Here's what would happen if you were to optimize this by this much. And what we were just talking about with auto tuning would be, clearly you can't just magically optimize things. So you'd have to do something else, like control the operating system, allocation of resources, allocation of threads, allocation of memory, and so on.
Yeah, I mean, it is interesting. I mean, because you're talking about system level, and there's also within the program, right? And so
yeah.
And I think the comment about profile guide optimization is right on, because really, in a way, it's just another approach to data-driven optimization, right? The distinguished software 2.0 from profile guide optimization is kind of missing the point, which is to say that we've always known that if we had more data about the runtime behavior, it would help optimize, right? And the real question is, like, how do you build that loop? How do you, are people willing to build the loop? I think the big pushback has always been with these things, you have to actually collect the data. There's a cost to collecting the data. There's a cost to the development process. There's expert overhead, and how do you update the profiles? I mean, there's all the sort of the details. The devil's in the details in these things. Conceptually, I think software 2.0 profile God optimization are sort of coming from the same exact understanding of being data driven.
Yeah, yeah. I think it was a missed opportunity in branding to not call it learned optimization.
Learned optimization. Okay, so we don't have other questions on the chat, so I'm gonna go off in a slightly different direction. Okay, so you talk about irrational exuberance, and of course, it's kind of sad because we can no longer be irrational. But let me just ask, do you think that we will see a new hardware paradigm that will shift that again? Because ultimately, you could just say, well, we just were on this incredible run for 50 years or whatever, and we got all this incredible performance boost. And now for the next 100 years or 1,000 years, whatever, we're just stuck. We're not going to do any better. We're going to have these giant data centers all over the world because we need all those cycles, and that's the best we can do right now. Or is there a different future there where you can see, you can see that that logarithmic curve continue?
I mean, obviously the answer is quantum, but yeah. I mean, look. Everybody hopes that there'll be some breakthrough that will allow us to, to sort of pick up Denard scaling again. There's plenty of very smart people who know much, much more about this topic than I do, working on, materials and, 3D stacking and optical and all of these sorts of things. I would like to be optimistic. It would be nice, right, to be back in that world. There's no question. Just, in terms of productivity, if you can just count on your program magically running faster because you bought a new chip, that's obviously great for everybody. I don't think that the current architectures, people have kind of given up. The approach that I think people have taken, which I think is pragmatic and appropriate, is they've identified kernels of things that are common and important and turned them into what they call accelerators, right? And so they have some chip or some part of an ASIC that does this, and that does this other thing, it does this other thing. And we have a very long tradition of doing this, right? Mm-hmm. So, you think about the old days, the IBM PC that I showed, right, from 1981 had this terrible processor, the Intel 8088, and it didn't, so when you invoked a transcendental math operation like sine, it would actually trap to software, and it would run a little assembly program. And so they then had a thing called the 8087, which was a separate chip. It was a math processing unit, right? And there used to be memory processing units. And then there's, there used to be vector computers, and now we have vector instructions. GPUs are being integrated into CPUs. So I think that it's not as nice, right, as like I take my code that does loads and stores and adds and subtractions, and now it's faster. But I think that there's plenty of opportunity basically by leveraging those sorts of things in the chips. And again, this is just the same thing as what's happened in Python, right? So here, but just at a different level. So here you have assembly code, right? Like traditional code, and it's like, oh, here's some functions that are now managed by hardware, and there's some hardware call we can make, like to a GPU. And at the high level for Python, it's very similar, right? It's like Python is really slow, but here's something that's a specialization, which turns out to be like NumPy, which is actually super optimized blobs, right? So I think that this strategy is like, I mean, it's what we've always done, and certainly it will provide benefits. But getting the C programs to run faster is, an unmodified C program to run faster is just a hard problem. And people in the architecture community, I just finished, well, I'm not actually done, but I'm co-chair of ASPOS this year. And it's widely recognized that improving single thread performance is great, but really seems to have run out of steam.
Mm-hmm. Yeah, no, this is certainly one of the things you see is all this all this interest and investment in thinking about how to make machine learning algorithms faster, right? So so instead of sort of saying we're going to make general purpose computing more efficient, we're going to actually focus on, say, inference. So let me ask you about that. I mean, I think that at some level, this is probably going to become more and more a mainstream part of all computing, is having the machine learning models. You know, what do you think about that future? You know, do you see that, you know, is this hype? Is this kind of like, you know, this year's you know, sort of interest, or is there sort of a long-term thread here that's going to make this part of every single computing, you know, every application?
Yeah, so I don't know about every application. Like I don't know if Angry Birds needs machine learning model, or your browser, but yeah, I mean, I think, look, I mean, Apple has chips now, right? There's ASICs that do some machine learning stuff. Obviously, it's a super accelerator. It's pretty standard now to have these things that you know, at least originally were called NPUs, so neural processing unit. And obviously Google has the TPU and all these things.
Yeah.
Yeah, I mean, I feel like for certain tasks, it's just a no-brainer, right? So if you're doing face recognition you can do face recognition in your phone, right? So I don't mean the little box that says, oh, this is a face.
No.
I mean who the person is,
Yeah.
right? Totally possible, right? And I almost certainly coming, right? Like, why do you need a server for that? You don't need a server for it, right? You can push it out to the camera.
Yeah,
and I'm sure there'll be all kinds of stuff like that.
Yeah,
Sorry?
same with natural language, right? You don't need to go back to the server to do Siri. Yeah.
Yeah, that's right. So I think that for the kind of the tasks that ML has had huge success at, it seems pretty likely that it's going to end up being a part of our everyday lives. There is obviously hype. I mean, it's not great for everything, and also deep neural networks are not necessarily the best solution for many problems, but they work very well for some problems.
Yeah, so we have a question from Dimitri. Did you want to ask it directly, Dimitri? I'm not sure.
Yeah, I can fetch. I was wondering, it's related to the comment about the shift to kind of specialized hardware. And I was wondering, do you think this should be an opportunity for PL research to try to provide construct at the user level, I mean, to the developers, to software developers, or do you think this strictly belongs to compilers, code generators, and the likes?
Yeah, that's a good question. So, so let's see. So first, I mean, the standard way that we deal with these things is through libraries. And then libraries, obviously, you have maybe FFI issues and things. But if you have a ton of work to do and not much data, then it works out great. And if you can do DMA or something, then you're fine in terms of memory. In terms of copying. So I feel like compilers and code generators, you know, they can do something, but it's like heroic efforts, right? I mean, if you look at, like, take a compiler, I mean, people have worked on the problem of array multiplication and all these sorts of like array calculations, I mean to say, for decades, like literally since the dawn of computing and optimization. And still today, if I write a program in the most modern, you know, C++ or God, I don't know, Fortran even, if I write it, the compiler is not going to produce anything that's within, you know, shouting distance of what the BLAS does. Right? And, you know, people have definitely worked on this. And, you know, my advisor, Catherine McKinley, and her advisor, Ken Kennedy, worked on automatic parallelization. That was actually reasonably effective in Fortran. And it's really, really, like think about, like, it took like 30, 40, 50 years of working on Fortran, which is a very well-behaved, easy to analyze language, to be able to automatically parallelize that code. And right now, it's still the case that people who do scientific computing with Fortran use explicit parallelism, like through OpenMP. So I feel like this is one of those like holy grails, like automatically parallelize my program. And we've never really gotten there. So I think that certainly, I'm not saying that we shouldn't pursue such a thing or think about it, but I feel like it's a very, very hard problem, and one that maybe is not practical in anyone's, you know, sort of horizon. So I think it probably makes more sense in the PL side to try to expose abstractions that are different. It's not just like ordinary straight line code, but are abstractions that a compiler can actually do something with. So imagine if you had a parallel 4, like you're telling the compiler, this is parallelizable, or it's okay with me if you parallelize it. It's a bad example, but you can imagine if there was some other thing, pretend you had some weird construct for operating on tensors, right? That'll be a lot easier to compile to efficient code than to try to recover it from individual index operations into arrays.
Interesting. Thanks, Dimitri. So again, I'm going to shift gears and ask you a little bit about some of your teaching experiences. I know you you had your student work on a project, Brianna DeVore McDonald, on the project Mossad, which was presented. You did a great job presenting it at UPSLA this year.
Did, yeah.
So you know, what motivated that line of work, that research, and just tell me more about your experience teaching computer science. I mean, it sounds like you know, this is something you take very seriously, and love to hear your thoughts about that.
Sure. So I'll talk about Mossad first. So so the reason that we were looking into it was that I was just you know, Mossad seemed unreasonably effective. Right? It's like, oh, it finds these things, and you know, people are doing these. You know, it's like, oh, it unearths cheating, and certainly we, you know, unfortunately, I've used MOS to uncover cases of cheating, and you know, it's not great, but if you don't run it, you don't find it. But I just was personally skeptical that this sort of static approach is, you know, is really that effective at rooting out all the cheating. So that was my sort of reason for going into it. I was like, well, I think we need something that's more dynamic, something that explores, like, compares the spaces through which programs run. I don't know. It's kind of like vague ideas, but I was like,
so were there
go ahead.
Were there instances where you were like thinking to yourself, I think this person's cheating, but I'm not catching them? I mean, was there sort of
yeah. So one of the things that you see sometimes is the disparity between exam scores and homework scores. And so when you see very high homework scores and very low exam scores, it's instantly suspicious. And so I had a student who did terribly on tests and fantastically on homework. And I was convinced the student was cheating, right? It's just like, this is clearly got to be cheating, but I wasn't able to find it. It's always possible that the student, you know, that he went out and hired somebody. Right. And then there's no way to know the cheating except to like give them an oral exam or something. So be that as it may, yeah, I'm not a huge fan of cheaters. Let's just say that. So, so what I wanted to know, I said to Brianna, I was like, well, you know, if you were to like pretend you're attacking Moss, let's see how hard it is to attack Moss. All right. And Brianna just like went away. She was like, okay. And she went away. She like read the Moss paper, and then she came back and she's like, I have an attack. And it always works. And I was like, so the original attack was you know, manual, and it was somewhat more naive. Like, we developed this approach, you know, over the course of some time, but yeah, that was the genesis of it.
Yeah, that's, I mean, so this strikes me as there's two different things that you're talking about here, both of which are actually very important. And both of which, the first one is the performance profiling, right? You know, super important. And, you know, and the fact that there isn't like a lot of investment, like from some like commercial firm or whatever, in building a great profiler is, you know, it's kind of shocking in my opinion, because again, it's like the cost benefit is there, right? It's like, if you build it, you know, it'll help millions of people and, you know, save lots and lots of code. I mean, lots and lots of compute time. But the same thing with the cheating, right? There's so many people that use Moss, right? And if you're telling me that, you know, you're maybe brilliant grad student can go and find an attack, you know, quickly against Moss, I mean, that says something about, you know, the robustness and also the amount of importance that people put on, you know, something of that value. It just strikes me as you know, problematic.
Yeah, I mean, I think the thing about Moss is I think that it's one of those instances of we want to believe. I mean, first, I mean, Alex, it's an Alex Aiken's project, right? And Alex is great, right? I mean, he's just, you know, super, super genius. And so, of course, we're like, you know, Moss must be super genius. I think most people don't know how Moss works. Like, they didn't understand what was going on. It just seems to be, it's almost like magic. It seemed to work so well. And you do want to believe, right? And also, I think faculty members want to believe that cheating is relatively rare.
Right.
Right. So I think that all the incentives are aligned in the right way for people to use Moss and to trust it. But, you know, that said, I mean, Alex actually thinks that it's quite possible that that people have actually employed this kind of attack in a manual way against Moss, that they somehow figured things out, or at least by kind of monkey coding, They eventually were trying to get their program to have a low MOS score.
Is it
so,
relatively easy for students to actually try out the MOS on their code without, you know, I guess you need,
it's a publicly available service.
You need another piece of code to compare it against. So that's the problem.
Exactly right.
Yeah.
That's right. So, well, I mean, if you're in the scenario where it's like I'm Chet, the cheater, and I have my friend Alice, who's a genius. I just need to convince Alice to give me her code, or steal it from her somehow,
right.
or get it from online, and then hack at it to see what I can do.
But just offline, they can download MOS. I mean, it's trivial for any student to get a copy.
You can't download it. It's a web service.
Oh, okay. So that does gate the usage, right? Because you could detect people that weren't, you know, professors in theory.
That's right. You could. That's right. And right now, Alex doesn't, and you could threshold it in some way, and that would be good. We actually also wrote, although we don't describe it in the paper, we wrote a mini MOS that implements. It doesn't implement the winnowing algorithm, which is the key thing that makes it scale. But we implemented the fingerprinting and whatever. And so, you know, in principle, you don't need MOS.
Yeah. Okay. Alexander has another question. What's your view on the best first programming language? And he sort of as a follow-on, starting from low-level languages versus high-level languages.
Yeah. So I do not agree with people who think that we should start from C or low-level languages. I think it's a terrible idea. I think that it's important. Like, I don't think that when we talk about the key concepts of computer science, we're talking about, you know, bit twiddling, for example, right? Or jumps. I just think that you want to engage with the big ideas of computer science early, and then show how they're implemented. I don't think the other way around makes any sense. So that said, I think it's really important that people be exposed to a mix of languages of different levels, of different kinds, and not just in a PL zoo class or something. I mean, in different classes, they should be using Python. They should be using some metal language. You know, maybe C++. I know people here are terrified of C++, but it is what everything is written in, ultimately, practically. You know, and JavaScript. Like JavaScript is the most executed programming language probably on the planet. And it's rarely taught outside of specialized circumstances. I think it's a fine language. It's broken, deeply broken in a lot of ways, but it's a way better teaching. Like, let me put it this way. Every browser is a full-fledged IDE. Every browser, like a shockingly sophisticated IDE with an incredible debugger. You have all of these facilities and inspectors and all this stuff. It's completely crazy. Like, I mean, Chrome is you go to developer tools and it's like a whole other app, right? It's incredibly sophisticated and it just ships. It's the regular thing. I saw Jonathan Bell, TypeScript. Yes, I like TypeScript. So actually CS Rankings is written in TypeScript. And we've used TypeScript extensively in my lab. And I would teach it to advanced students. I still feel like the ergonomics of the language leave something to be desired. It's fine to go from JavaScript to TypeScript, though, gradually, if you will.
So,
and then imperative versus, I see it on the thing, imperative versus functional, performance and for teaching. Look, I think that, you know, really there are languages that are used and there are languages that we talk about here in conferences and so on. And yes, it's true that there's some people who are using Haskell, but you know, look, for undergrads, honestly, we need to keep in mind, we are educating them, but you know, programming is a skill that we're providing for them. I mean, I teach at a large public university. 95% of those kids are going to software development positions. And I feel like, I mean, there's this typical sort of, should we teach in this, and is this driven by industry and whatever. I mean, I think it's fine to teach a functional language in some context. I mean, I actually, I spent a year in England. I learned Miranda, which is a predecessor to Haskell. I like it a lot. I think it's rough in a lot of ways for students. The type system is kind of a nightmare. You get these terrible messages and it's like, oh, this is, you know, it's great that there's this whole like lattice of arithmetic types, but I mean, for a freshman, it's a catastrophe. So I actually think that having untyped languages, well, untyped, you know what I mean, non-statically typed languages for early classes especially is just fine, and actually completely reasonable. And but it doesn't mean that we can't also be including, you know, languages with more types. Now, of course, there's functional programming like Racket. That's something that you need special people to do, since not everybody is as familiar with that ecosystem, but that's another possibility. I only say that because Jonathan asked the question. Or said TypeScript, so. The other question from Alexander, though, was about performance and teaching. Again, I think it should be a mix. I think that you should, I think performance is one of those things that, you know, look, debugging is hard. Performance debugging is harder, right? Like debugging, the thing is wrong. Go find the thing that went wrong, right? Performance, like the program is too slow. It's a global property, right? And so, you know, debugging global properties, you know, that's hard, right? Like you're looking for something that's functionally correct, let's say, and it just is running too slow. So I think that this is something that we should be teaching our students, certainly to use profilers to understand what's going on with performance, to understand what goes into performance. Like if you're reading one character at a time from a file, it's going to be a disaster, right? In Python, I've seen this. Like you see this all the time in student code, right? People will be like, I will read a character, right? And it's like a library call, like every character. You know, you could speed the program up by 100x just using reading everything into a buffer, right? So there's like basic stuff that transcends languages that I think would be very useful skills for students to have.
So we're almost out of time, but let me just ask one final question. I know you've done tons of work for the community, including your csrankings.org. Can you tell us a little bit about that, the experience, why you built it, and how it's going? And thank you, for creating it.
Oh, thank you. Thanks are relatively rare. So I think that I and so many other people were frustrated with the situation with the CRA rankings, and especially with US News. And the fact that this you know, terrible former news organization was somehow controlling our destinies. And they had this ranking that was basically a survey. Like I saw the survey one year, and it's ridiculous. It's just like, you know, a Likert scale for all of these institutions, and it was given to the department chairs and to deans, right? So what are the odds that the dean, unless you're in a college of computing, knows anything about computer science? So essentially they just picked wherever they went, like wherever their husband or wife went, wherever, you know, other people went, and then famous schools. Right? Schools that are good in their discipline, like physics. So completely terrible methodology. And, you know, I tried to come up with something that I felt would be useful for graduate students. So the ranking part is an unfortunate necessity. People, like, you have a search engine. Search engines don't just report everything. They rank them. You have to rank things, right? So if you're doing information retrieval, you need to rank. And so it's inevitable that there's going to be some ranking. But, you know, it's a way for people to dial in based on their research area, to find faculty members who are working in those areas, and then learn about the research and maybe go to that school. I think that, you know, people who go to do their undergrad at, you know, places that are already super established research institutions, they can get guidance from faculty advisors who know the field and know the area and have some sense of these things. But if you aren't in that privileged position, then you're out of luck. I mean, when I was an undergrad, I grew up in Florida. I had a scholarship to the University of Miami. I went looking for grad schools. I had no idea what I was doing, right? And people, you know, undergrads at University of Miami never went to grad school. It just wasn't a thing. So there was nobody to give me advice. Now, of course, the internet, the web didn't exist then either. So certainly CS rankings couldn't have existed. But having a resource which would have allowed me to go, I'm interested in programming languages. Where are the schools where they're doing programming languages? What does the research look like that they're doing? That would have been very useful. I luckily stumbled into UT Austin, and it all worked out. But I feel like, this is, yeah, I mean, I think that the value proposition for CS rankings is not so much the ranking, which, like I said, is inevitable, but the way that you can quickly find people who are actively publishing in the top conferences.
Yeah, no, thank you for doing that. And I agree. I think it's the fact that it's a ranking gets, it's kind of up front, but in reality, it's really the process and the support it provides to people who just want to have some basic understanding of what the grad schools are doing and where people are, et cetera. So I think that's a really insightful. I think it's 8:20. I think in theory we're officially out of time. I don't know how these Zoom meetings end, so I'm gonna say thank you. And again, very interesting presentation, and also a great chance to chat with you and sort of.
Yeah, absolutely, great as always. Thanks for the hard questions.
Oh yeah, no problem.
So by the way, I'm going to advertise for something else. So I'm off to host the UMass Systems Lunch. So Gun Searer is going to be there talking about. So he has this startup called Ava Labs. So he'll be talking about their, let's call it, Bitcoin replacement called Avalanche. And Gun is superstar in distributed systems. So if you're at all interested in that, I highly recommend. That'll start at noon Eastern Standard Time. And I will be, so if you go to systems-lunch.org, you can sign up. You'll get invited to the Slack. Otherwise, I'll tweet out about the YouTube link momentarily.
All right. Well, thank you, Emery, and thanks for all the things that you do for the community.
Thanks so much.
Really
all right. Bye, everybody.